Okay, good morning everybody. So let's get started. So my name is Rob Fender and I will be lecturing you for the next 12 lectures on the subject of vector calculus and multivariable algebra. So this course introduces a few things which you'll not have seen in A-levels, in particular surface integrals, div, grad and curl. And these are tools which, as physicists, you'll be using a lot in subsequent courses. There is an unfortunate, or slightly unfortunate, overlap of courses in that some of the stuff I'll be teaching you and deriving, actually you'll be using at around the same time in your first year electromagnetism course with Neville Harnu, but then again, it doesn't really matter if you see something twice. In today's lecture, I'm going to essentially go through I'm going to give a summary of the content of the course, and then we're going to do a little refresher on vectors, which of course is a very key component of this course, and then we're going to end with a brief description of what scalar and vector fields are. So a lot of this course is about using vectors and using fields to describe things and understanding the properties of those fields and how you can measure quantities within those fields. Okay, so this is the course. Here's a laser. Okay, so here's a pathetically weak laser, which I'm not going to use. So this is a summary of the course content. So today we're going to do a review of vectors, and we're going to discuss what vector and scalar fields are. So I won't dwell on those any further because we're going to come to them later in today's lecture. Then we're going to talk about multivariable integrals and the Jacobian. So in multivariable integrals and the Jacobian, these are things which you'll be quite familiar with and you'll get to understand quite quickly. In fact, we'll cover nearly all of the content of multivariable integrals and the Jacobian in tomorrow's lecture. But essentially, you are used to doing integrals in one dimension. So you are used to having some function of x, which looks like this, and you are used to the fact that the integral of x between some limits tells you the area underneath that graph. In the case of multivariable integrals, what we're essentially doing is we are expanding our integrals to work in more than one dimension. So in this course, we will do a lot of two-dimensional integrals. And a two-dimensional integral can be simply thought of as something where you have a function of x and y. And so the height here would be some function of x and y. And this means that at every point above your x and y plane, this function has some value. So you have some surface which is projected up above the x and the y plane. And your multivariable integral, your integral in terms of x and y, would be the projection of your region of interest in the x and y plane onto that surface, and it essentially gives you the volume under here. And of course, the 1D integral is simply the area. So these are all things that you know very well, and we'll be able to go through all of the materials I'm doing 2D integrals tomorrow. We'll also discuss how to do 3D integrals, but there's not very much use of 3D integrals in this course, and in fact, they're just a very straightforward and logical extension of doing the two-dimensional integrals. The Jacobian is something that you will be familiar with, at least in the one-dimensional case, and the Jacobian tells you how to change units from integrating in one variable to integrating in another variable, okay? And then the Jacobian, which we often use in this course in the two-dimensional case, will explain to you how to do integrals where you initially start in an X and Y coordinate system, for example. So this would look something like this. And then you want to convert to another coordinate system in which either the problem which you're trying to deal with has been described in that coordinate system, or perhaps you want to switch to a coordinate system which is more natural for that problem. For example, if you have radial symmetry, you'll want to switch to plane polars or perhaps spherical polars. So then you may have some coordinate system which we'll call U and V. So these are lines of constant U, these are lines of constant V. And in order to be able to switch between our coordinate systems, so for example, knowing what a unit area is in our X and Y plane, and then switching to a unit area in our UV plane, this requires the use of the Jacobian, which essentially, at least at the level we use it, it's a fairly complex thing, at the level we use it, allows you to understand how to switch between coordinate systems. We will discuss differentiating vectors, and we will discuss line integrals and conservative and non-conservative fields. So a line integral is essentially a generalization of the normal 1D integrals which you are used to doing. However, instead of just knowing that your integral stretches between two limits, for example, in the x coordinate, then you can have an integral which describes some path, let's say, in your xy plane, and at each point in your xy plane, that path, your variable, which is a function of x and y, has some height, so essentially you are integrating along the path of your line integral. So it's very, very similar to the standard one-dimensional integrals that you're used to doing, but you need to correct your path in your coordinate system to real lengths. So conservative and non-conservative fields describe two different types of scalar and vector field and the relationships between them. So conservative fields are something which will come up a lot in your electromagnetism course. Essentially, a conservative field is a field where when you move between 2 points, for example, in a potential, then the energy difference in moving between those 2 points does not depend on the path that you take. A conservative field also has the special property, as I'll show you later on in the course, that it is the gradient of a scalar field. So I'll come back to this in the final slides of today's lecture. But a scalar field is a field where essentially, in however many dimensions you have a numerical value at each point in that field. And a vector field, of course, is a field where you have a vector with a direction and a magnitude at each point in that field. A conservative vector field is actually a vector field which is the gradient of a scalar field. So this is a particular type of vector field. The electric field and the gravitational field are examples of conservative fields. And we will understand how to tell whether or not a field is conservative or non-conservative. Okay, so there are three newly introduced mathematical terms then in this course. The gradient, the divergence, and the curl. Have you already had your first lecture or lectures in electromagnetism? Has he already got to the gradient? Yeah? Okay, right, good. Well, not good. So the gradient I will be discussing in perhaps a bit more detail than the electromagnetism course, but you'll already know that the gradient tells you about the direction and magnitude of the rate of greatest change of a scalar field. So the gradient is something which acts on a scalar field of however many dimensions you want, and the gradient takes a scalar field and converts it to a vector field. The gradient takes a scalar field and converts it to a vector field. The divergence acts on a vector field and returns a scalar quantity. And what the divergence does is it tells you how much your vector field is flowing in or out of a given point or given region in your vector field. So as we'll return to later on in this course, and I'll show you a brief example later on in this lecture, you know, we can describe vector fields, for example, a two-dimensional vector field may look something like this. There are vectors with magnitude and direction at every point in your vector field, and the divergence basically says that we take some infinitesimally small region in that vector field, and we calculate what is the surface integral of the vector field as we shrink that radius down to 0. So that essentially tells you how much that field is flowing in or out of any given point. And then finally, the curl, which we won't get to until the final third or so of the course. This tells you, this takes a vector field and returns a vector field. And this tells you how much your vector field is rotating at any given point. So again, for ease of drawing, I'll give the example of a two-dimensional vector field. So I may imagine now that I have a vector field that looks like this. And the curl is the case where you take a region in your vector field, and in the limit that this boundary shrinks down to infinitesimally small, you work out the line integral of the vector field around that boundary, and that actually tells you the direction and by how much your field is rotating at a given point. Okay, so those are the three new key mathematical tools which you're going to get introduced to in this course. A key component of the course, and also something which tends to constitute quite a large fraction of the exams when you come across to them, is surface integrals. So in the case of surface integrals, you will be wanting to work out what is the, for example, what is the flux of a vector field through a given surface. So I'll just give you another example here. I may imagine that I have some vector field, so again I have the direction and magnitude of my field at every given point in a three-dimension. So there are vectors everywhere, and then I may construct some surface for whatever problem, whether it be abstract and arbitrary or whether it actually appears to have some physical meaning, and you want to work out what is the flux of the vector field through that surface, okay? And these are surface integrals, and we do a lot of these. The divergence theorem, returning now to the divergence theorem tells you that if you have a three-dimensional body existing in a vector field, that the volume integral of the divergence flux. So what that means is if I have a three-dimensional surface embedded in a vector field, within this vector field, at each point I am able to measure the divergence. So I can measure the divergence in all my infinitesimally small little volumes, and that tells me how much the vector field is flowing in or out at all those given points. And I can also measure the flux of the vector field integrated over the surface of that three-dimensional shape. And I think it's probably intuitively obvious, but we will of course derive it formally. It's intuitively obvious that these two things should be equal, right? So the sum of the inflow and outflow of the vector field within that volume equals the flux through the surface of that volume. And that's called the divergence theorem. And that's one of the two key theorems which we'll address in this course. And then the other one is Stokes' theorem. And Stokes' theorem is similar. Good. So Stokes' theorem says, and I'll now illustrate this in a two-dimensional case. Stokes' theorem says that again, if I have some surface embedded in a vector field, then the sum of the curls within the area of that surface. So remember, the curl measures the rotation of the field at every point. The sum of all of those curls equals the line integral around the boundary of that surface. So the sum of the curls, or the integral of the curls, equals the line integral. And that's not much less intuitive, I think, than the divergence theorem. You may imagine your vector field is rotating a lot in here, but the net amount around the boundary of your surface will be just that you can measure doing the line integral. Okay, and then we'll finish the course in about week 7 by doing the second order vector operations. So I should note also, and I guess you've already looked at your timetables, the scheduling of the course is slightly unusual this year, so we will have 2 lectures this week, 3 lectures next week, and then there will be no lectures at all in week 3. So hopefully you've all spotted that. And then we'll return in week 4 and we'll carry on through till week 7 to finish the course. All right, good. The course notes are available online if you go to, perhaps you've already got a link from Karen to somewhere else, but also if you just go to my homepage, there's links in the top right-hand corner. I don't know whether you've started doing the problem sheets for this course yet, but you will note when you do the problem sheets for this course that sometimes the material goes a little bit beyond what we describe in the lectures, but that's good. There's only limited time in the lectures to go through things. And also, if you go to my homepage, my course notes are available to download. So hopefully you'll find my course notes quite useful, and they do describe the course more or less in the sequence in which I teach it, which you might find helpful. But I would also recommend these books for the course. So, of course, I think you've probably all got copies of Riley, Hobson and Bentz, which is the standard mathematical text for the first and second years. So this covers all of the material which I'll be covering in this course. However, I do find that it's very, very terse. It covers it very, very briefly. Okay, so things like the gradient it will cover entirely in about 1.5 pages. So if you're fine with that, then that's a great book. But if you want a little bit more discussion of why these things are like they are, then you might want to consider, as well as my notes, one of the other 2 books. So Pearson, Griffiths' Introduction to Electrodynamics, you may already have, or you will certainly have when you start doing your second year electromagnetism course. Since you will have to buy it for next year, you may as well buy it now. And the introductory chapters in Griffiths actually have a very good and clear discussion of vector calculus. And finally, if you want to look at things a slightly different way, but again very clearly, there's this book by Shea, Div, Grad, Curl and all that, which I would also recommend if you have infinite spare time and infinite resources. Okay, so let's do a quick recap of vectors. So this part of the lecture should essentially just give you all a nice warm glow, because you should understand it all already. So a vector has a direction and a magnitude. In fact, let me stop now and make the point that you will see me several hundred times during the course drawing this diagram to illustrate a three-dimensional space. Please get used to the habit of orienting your axes the correct way. Okay, so this is I, this is J, and this is K, or in other words, this is X, this is Y, and this is Z. That's a right-hand coordinate system, and it messes things up a bit if you get it the wrong way around. Okay, so a vector, as you know, it has a direction and a magnitude. A unit vector has a magnitude of 1, as you all know, and is represented by a hat. So the unit vector, for example, the unit normal, which is something we'll see in a moment, that is the unit vector perpendicular to a plane, is illustrated like that. So that's a vector in the direction which is perpendicular to the plane with magnitude 1. So vectors are generally described in terms of their three components. So again, this is the Cartesian coordinate system which you're very familiar with, x, y, and z, and I would typically describe my vector f as perhaps the x component times the unit vector in the x direction, the y component times the unit vector in the y direction, and the z component times the unit vector in the z direction, or the k direction. The two other main coordinate systems which we're going to use in the course are spherical polar. So the spherical polar coordinate system looks like this. And again, this is pretty straightforward, but causes problems quite often at times. So please make sure that you understand how to draw this. And again, we'll return to this later in the course. So here's x, y, and z. The spherical polar coordinate system has a polar angle. This projects down onto the xy plane, where you have an azimuthal angle, and it has a length. Okay? So in spherical polar system, you transfer to a length and two angles. And we choose to use the spherical polar coordinate system, or its simpler two-dimensional equivalent plane polar, when we have problems which have some kind of radial or spherical symmetry, obviously. And then the other coordinate system which you'll come across is the cylindrical coordinate system, which we don't use as much, where you essentially have a plane polar coordinate system. So in this case, some point is represented by some angle, phi or theta, and some length r. So this is plane polar, and then it has a height, h, as well, or z. And the cylindrical coordinate system is typically used, not surprisingly, for situations where we have some kind of symmetry along a particular direction. And what you'll see later on in the course is that a lot of the problems which you'll be tasked with doing, and which will come up in your exam, actually can be approached using, essentially, and not surprisingly, any of the coordinate systems. And part of the trick in turning a problem from a problem which takes you 5 minutes to one which takes you half an hour is understanding which coordinate system is most appropriate for a given problem. Okay, adding and subtracting vectors, that's very obvious. I'm sure you know about this. So if you want to add together two vectors, then you just add their x components, you add their y components, and you add their z components. If you want to know what is the vector that is pointing between 2 points, then the vector which points between 2 points, the vector, as you see here in the diagram, that know all of this. You've known all of this for at least a year, no more. Okay, so here's a quick example, which you may already have done in the electromagnetism lecture. And this is an example simply showing the principle of superposition, which is relevant for electromagnetism, and also showing how you use vectors. So the question says, the electrostatic force on a charged particle Q due to another charged particle, small q, is given by F is K, which encapsulates the 1 over 4 pi epsilon naught. Q, R, which is the unit vector in the direction between the two charges, divided by R squared, which is the distance between them. And actually, as we'll see later on in the course, this is nice. This is a manifestation of a conservative field, which is the gradient of the electrostatic potential. So the question says, write down an expression for the force on Q at some position vector capital R due to n charges, Qi at Ri, where I is some large number. So what we say is that we have some large charge Q at some position vector R, and we have a whole bunch of other charges, Q1, Q2, Q3, Q4, etc., around this. And we want to know what is the electric field at Q due to all these other charges. So first off, we want to work out what are the vectors from these individual charges that are felt by the large charge Q. So the vector between each of these points and the charge capital Q, the vector between those is given by that. So I always have to check to get it the right way around. That's the vector that goes from Qi, from charge Qi to big Q. And then the sum is simply K, which is our constant 1 over 4 pi epsilon naught, the sum over all of the charges, big Q, little qi, the vector divided by the magnitude of that vector. And what we've done there is we've simply used the fact that we can replace the unit vector in a given direction by the vector itself divided by adding another term of its magnitude on the bottom. Okay. So that's a very obvious example of just using vectors, adding vectors together to work out via superposition what the total field is at some given point. All right. So again, some things which you already know. The dot product of two vectors is a scalar, and that is the projection of B onto A. So if I do the dot product of those two vectors B onto A, then essentially what I get is this. Okay? And that's the projection of B onto A. And again, you know this is a scalar. If you wanted to write it out algebraically, then you would have the X Y and Z components multiplied together and then added together. And again, you know this. The vector or cross product of two vectors is illustrated in this diagram here. So now if I have two vectors, call them A and B, the cross product of A and B gives me the area of this parallelogram. And because this is a vector product, then it has a direction. So in this case, I've drawn these the other way around. So in the case I've drawn here, A cross B would give you the area of this parallelogram and would be a vector which is pointing into the board. If I do B cross A and I get the same area, then it would be the vector pointing out of the board. And then the algebraic approach, so if I write this again now, for example, in terms of vectors f and g, then the algebraic approach would be that I would have fy gz minus fz gy times the unit vector in the I direction. Fx gz minus fz gx in the j direction plus fy gz minus fz gy in the k direction. What? Yep, that's x and y, sorry. Now, as you all know, this result can be expressed as the determinant of a matrix. So the cross product is the determinant of a matrix. I'm sure you all understand how to do the determinants of matrices, but this is something which comes up again and again in the course. You'll need to know how to do the cross product. You'll use the determinant of a matrix to work out what the curl is, and you'll also use the determinant of a matrix to work out what the Jacobian is when you're doing coordinate and variable transforms between different integrals. So A cross B is the determinant of the matrix I, J, K. And as you'll have seen from the previous example of the cross product, we quite often have cases where we're working out the cross product of things which are in a plane. So that essentially means that they will have no k components, but the resulting vector will be in the k direction. All right. The scalar triple product gives you the volume of the parallelepiped whose sides are given by the vectors a, b, and c, and this is given by this expression here. This is something which comes up occasionally in physics, so you might want to know this one as well. There is a vector triple product, and that essentially never turns up in your physics degree, so you don't need to know that one. Okay, so here's some important properties of vectors which you will need to know. So in terms of the dot product, the dot product, as you know, of orthogonal vectors is 0. And that makes sense when you have two vectors which are orthogonal. There is no projection of vector A onto vector B, and so the dot product of them is 0. The dot product commutes. So this means that A dot B is equal to B dot A. And And as you know, this is not a property which the cross product shares. It distributes. So this means that A dot of B plus C equals A dot B plus B dot C. And it multiplies by a scalar. So for example, lambda dot A dot B equals lambda A dot B. So the cross product, as you know, of parallel vectors is 0. So for the scalar product of orthogonal vectors is 0. In the case of the cross product of parallel vectors is 0. It anti-commutes. As I've already mentioned, so this means that A cross B is equal to minus B cross A. In other words, you get the same area, but it points, the resultant vector points in the other direction. Okay, and then finally something which is also important in this course is understanding planes. So there are a number of different definitions of planes. Okay. So first off, definition 1 of a plane. If A, which is a vector, is in the plane, and B and C are non-parallel to each other, but parallel to the plane, then the position vector of a point in the plane is given by A, which takes you to the plane, and then any other point in the plane can be described by some scalar multiplied by B plus some other scalar multiplied by C. So what that means is that if I have my coordinate system and I have some plane like this, for example, then my position vector of some point in the plane is the vector sum of the vector taking me to some point in the plane, which is A. And then vectors B and C are parallel to the plane. They don't have to be in the plane, right? They just have to be parallel to the plane. And because they're non-parallel themselves, then any other point in the plane can be described by a combination of B and C. So for example, making it very easy, I would say that B and C were non-parallel or even orthogonal vectors in the plane. And then any point in the plane can be described as the sum of A plus some amount of B and some amount of C. Okay. Second definition of a plane, which is essentially equivalent. Three vectors, A, B, and C, all lie in the plane. Then the position vector of any point in the plane can be given by A, which takes you to the plane, times by some scalar multiple of B minus A. So A, B, and C are all in the plane, so the vector B minus A is also a vector that's parallel to the plane. So it's some scalar multiple of some vector which is parallel to the plane, plus some other scalar multiple of another vector which lies in the plane. So these, the B minus A and the C minus A are equivalent to the vectors B and C in the previous example. Slightly less intuitively is the following. If the unit vector to the plane is n hat, and A is a vector in the plane, then we know the following. We know that R, which is some point in the plane, the vector from that to point A, which is also in the plane, the dot product of that with the normal to the plane, which is then going to be orthogonal to this vector, equals 0. Because the dot product distributes, we then know that R dot n hat equals A dot n hat. And this actually equals a constant. And that constant is the shortest distance from the origin to the plane. And just to illustrate why this makes sense, if I just do a simple two-dimensional example, here's my origin. Here I have some plane, and here I have my unit normal to the plane. Then I can see that the shortest distance from the origin to that plane is like this, okay? And then the dot product of R and n hat will give you the distance from the origin to that plane. But if I pick some other point in the plane, for example here, then I can still see that the dot product of that vector with the unit normal to the plane is still going to have the same length, okay? The projected distance of that vector in the direction of the unit normal is still going to be the same, okay? So the dot product of the vector to any point in the plane, the dot product of that with the unit normal to the plane gives you the shortest distance from the plane to the origin. Okay. So these are useful things to remember. I said all of this. The thing I didn't write on the board is also the fact that the cross product does not associate, okay? So A cross B cross C in brackets is not the same as A cross B in brackets cross C. Okay, and these things I said, all right, so a plane can be defined in 3 ways, which I've gone through on the board, and this is in the notes as well. All right, and this is the reason why it works for the perpendicular distance to the plane. Okay, so here's an example then. So just to prove that vectors are independent of the coordinate system, and to give the useful example of the rotation of a coordinate system, what we want to do is we want to imagine that we have a coordinate system which is initially given by x and y, and we now rotate this coordinate system through some angle. So I now rotate my coordinate system such that I have axes x prime and y prime. And I've rotated my x and y coordinate system through some angle theta. Now I know in plane polar coordinates in my original coordinate system that the x component is the length projected onto the x-axis by some angle which I'll call phi, okay? So I have some point over here. There is some angle phi. I'm using either distinguish it from the rotation angle theta. So we know that in our original coordinate system, the length of x was r cos theta, and y was r phi, and y was r sine phi. So we now can see that in our rotated coordinate system, x prime is r cos phi minus theta, and y prime is r sine phi minus theta. So x prime is r cos phi minus theta, which is r cos phi cos theta plus r sine phi sine theta by the double angle rule. And we know that this equals x, and we know that this equals y. So we see that x prime equals x cos theta plus y sine theta. And we can do the same construction for y and y primed, and then we end up with the result as given on the board, that fx, fy, and fz equal cos theta sine theta 0 minus sine theta cos theta 0, 0, 0, 1 for a three-dimensional rotation through a plane polar angle of theta of my coordinate system. Now, a nice thing to do when you go away from here, if you're interested in checking for yourself that this is correct, is you can project these distances down onto your axes, and you can work out geometrically these results and show that they are correct. Okay, so very, very quickly then, I want to touch on what scalar and vector fields are. I think they're pretty obvious from their names. A scalar field is a field where at every point in the field there is a numerical value, there is a scalar value which represents the field. So an example could be the picture on the left, where this is a temperature map of the UK in January 2016, showing the distribution of temperatures around the country at a given point. So at any point in the country, if this was actually described mathematically by a field, at any point in the country you could say, what's the value of the field here? There would be a number, and that is the temperature of the field at a given point. A vector field, however, as I've already described, is a field which at every given point there is a vector, and this may be two-dimensional or three-dimensional in the examples we'll do in the course. This has a magnitude and a direction, and that tells you about how the field is flowing. And perhaps the easiest way to think about this is perhaps think of the vector field as describing how a fluid is flowing. Okay, so this is, in fact, that is the case here. These are wind speeds which show you how on a particular given day the wind was flowing around the United Kingdom, and that's an example of a vector field. And I've no idea what's happening to that particular bit there. That's at the bottom of Ireland. It's very strange. Okay, so here's some example of simple vector fields. If you could all write these down and then have a go at we haven't got time now, have a go at sketching these. It'll take you about 2 minutes, I think, to sketch out what these fields look like so that you have an idea in your heads how to think about vector fields. And I will quickly come back to these tomorrow, but I'm sure you'll all manage to sketch these out. And then tomorrow, in tomorrow's lecture, 9 o'clock on a Friday morning, we're going to discuss how you do multiple variable integrals, which again is, here's an example. We have some field which is a function of x and y, and when we do the multiple variable integral, the integral over x and y of that, we are actually calculating the volume under some region. So those are those vector fields. Write those down and have a go at sketching those, and I'll see you tomorrow morning. Thank you.